Okay, the record is now on. So this is where we left off last time. We started talking about the failure of the tension members. Okay, so when you put the member under tension, be mindful that we are talking about the two force member, so to speak. Okay, so this force is the axial force in the axis of the member. We can have one of the two failures. The first one is the tensile yielding of the cross section. Okay, so whenever your member is under the force, oops, sorry, I can redraw that again. Okay, it can yield anywhere. Okay, but let's say if the member doesn't have any hole, it means that it is very highly likely that the member should yield before it ruptures, right? Because if you don't have a hole here, the area that is going to rupture will be the gross area. And naturally, when the rupture is going to occur, it is going to be the ultimate strength. But whenever you have the hole, your section will be reduced, right? Because you have to deduct the area that you lose because you punch a hole in the member. If that is the case, the rupture may occur at this net section. Oops. Oh. And this net section may rupture. Now I got a very good question from your friends via an email that we can only have these two failure. Like he was wondering if yielding was possible at the net section. No, it's not going to be possible because just look at the nature of things. When you punch a hole, the area is reduced. It may, naturally speaking, it may yield a little bit, but it's going to be, very short. But all of a sudden, it's going to rupture because you already reduced the area. So when the area is reduced, chances are this is not going to yield anymore. It's just going to go ahead and rupture at that area right away. So basically, when we talk about, the member under tensile axial force, we have two major failure modes. Either one of them is going to occur with your member. Okay. So now let us take a closer look at the tensile rupture in the net section. When you take a closer look, you see that this is after we deduct the area that we may lose due to holes and so on and so. So the gross area, when deduct the hole, it becomes a net area. But note that this is not the net area. This is the effective net area, meaning when you are having a hole, you of course want to try to connect the members to the support, to another member because of the splice, for whatever reason. You lose the area because you want to make a connection. That's the point. And when you do that, not only that you lose some area so that your gross area become net area, there is another phenomenon, that's a singular. That's not a phenomenon that may cause your net area not to carry the force 100%. Okay, so I can say this phenomenon that may cause the net area to not carry the load 100% of the net area. Okay, this is the phenomenon called shear lag. Okay, so let's before we get into that, let's say the summary is this is pretty simple, right? The ASD, we calculate the nominal strength. Remember the nominal strength or the calculated strength, or the maximum capacity that you can get, and then you reduce that to design strength by divided by factor of safety, it's ASD, or you multiply that by the reduction factor if it's the LRFD to get the design strength. So the N is nominal, this is the design. Okay. I'll try to stick with the ASD because that's what the Thailand Building Act has for the demand side or the load side. Okay. So now let's take a look at this. Okay. This is the example of that shear lag behavior. So let me emphasize this a little bit. Let's take a look at this. This is the side view of the angle. And what you see here, this is the bolts. Okay, so that means this angle is going to be attached to some kind of support. Maybe it's a plate here or something. So if I draw the, let's say, let's call this front view, okay? If I draw this view, what you see is going to be the angle itself. And then you have bolts here, and then you have the plate as the support. Okay, that's a front view. And if I draw the top view, you're gonna see the angle. That's the thickness, right? And then you have the bolts like this, and then you probably have the support like this as a plate. Okay. So what happens is this: the force is like water. Okay, it's just going to try to flow wherever is most convenient for it. Okay, you cannot talk to it. You cannot tell it, hey, come this way. Come on, believe me, come this way. The force doesn't talk to you. It just goes wherever it wants to go. So when you have the connection, generally, if you believe in statics, it means that this force is going to travel through the centroid of the member. Even though if you may already know that the centroid of the angle is in the air. That's where the force is. You know, the force is going to be at the centroid of the cross section, right? And when it reaches the connection, it will try to flow through the bolts as soon as it can, so that it could just continue its travel through the centroid and then down to the bolts to the next path, like that. Okay. So when it wants to do that, that will be the area that it doesn't want to go, right? It's like you want to walk to your destination, and then somebody say, hey, try to walk as long as you can before you reach the destination. You don't want to do that, right? So just like the force doesn't want to go into some area where it's too far away from the connection. It wants to go into the connection and then moves on to the next member or to the support as soon as possible. So when you see this is the critical section, because when the rupture is going to occur, it is always going to occur at the first bolt hole. You know why? Because when you look at the free body diagram, let's say if this is your force, tension, T maybe. When you cut the free body diagram and you look at the bolts, let's say if we have 3 bolts, just like this picture, it means that each bolt will take 1/3 of the force, right? T over 3. Now 3 comes from the fact that we have 3 bolts in this picture. So at the first line of the bolt hole, the force in the member is still T, right? Because you don't have anything traveling down the bolt yet. But when you move to the second line, 1/3 of the force already moved through the first bolt. So at the second line, you only have 2/3 of the force left in the member. This is basic free body diagram. So that is why if the rupture is going to occur in the member, it will always occur in the first line of your bolt, correct? It can never occur in the second line, because if you talk about the second line, it means that you already have 1/3 of the force traveling down the first bolt. So we always going to have the failure at the critical section at the first bolt. Any question on this one? Are we crystal clear then? Let's hope so. Okay. So you can see now that if we look at this critical section at the first bolt, okay, you see that this area is the area where the force doesn't want to go to. So it doesn't carry any load. As a result, it becomes ineffective. So you see, when you look at this green critical section, not only that you lose the area deduction due to the hole here, but you also have the area of the member where the force doesn't want to go. So when you look at this, you deduct the area due to the hole, and then you have the net section, hole deduction. You also have this ineffective area as well. So A net is further reduced. All right. So let's take a look at this. Compare the second picture, the picture down here with the one up front. You see that for this member, the length of the connection that we have is longer than the top one. You can see it probably has 1, 2, 3, 4, 5, 6 bolts. So the force has a better opportunity to make a transfer from the centroid of the member into the connection. So the transition is smoother because the length of connection is longer. Just like when you drive a car and you don't have to make a tight turn, you see, the radius of your turn is wider, so you change the lane smoother. But in the first picture, you see, you only have this much to change the lane, the force changing the lane from this member to this. So the change occurs in a very tight manner because you only have this length to change the lane. It's tighter. So the force transfer is not smooth and you lose this area. But when your connection is long enough, you can make a very, very smooth transition from the center of this member into the connection. And so you don't lose much. And from this picture, you see at your critical section, you almost lose nothing because the entire net area is completely effective. Okay, so if this is the case where you probably have the area that becomes ineffective due to the short shift of the force from the member to another one, you may have to reduce your net area further due to this phenomenon that we call shear lag. Okay, keep in mind that the funny thing is we are talking about tension failure, right? But the phenomenon itself is called shear lag. I don't know who came up with the name. Now I still don't see why it's called shear lag, because it's a shear in the bolt. I don't know. I don't want to make a guess, but we're just gonna have to go by the flow here because there's no more reason that I could offer you. So you may have to reduce the net area further by the factor called U, or shear lag factor. Now, generally, the shear lag factor is very simple to calculate. It's 1 minus X bar over L. See, L is the length of the connection. So be careful, it's the length of the connection, meaning if you look at this picture, it should begin from the first bolt down to the last bolt. Likewise, this one, from the first bolt to the last bolt. Okay, that's L, which is the length of the connection. X bar would be the distance that the force has to travel. In this case, just look at my front wheel. You see that the force will have to travel from the centroid of the member to the face here where the connection is. So that becomes the distance that the force has to travel. In other words, it's just the distance of the centroid of the member or X bar. Okay, so X bar, you can say that yes, it is the property of your cross section. If you can get your hands on the property of the cross section, which I just posted a few minutes ago, so maybe you can download it now while listening or during the break. Okay, pardon me for not doing it earlier, because I don't think we're gonna use that a lot today. That's why I'm just posting it. Okay. So that becomes a distance. It's a property of the section, so it's a fixed value. What you can play now would be the length of the connection. Okay, and you can see if the length here is small, short connection, so to speak, just like this picture. This is the denominator, right? When you have the small denominator, this component becomes large, correct? Because the denominator is small, so this number is large. So you're gonna have the shear lag factor way less than 1 if this portion is large. Now, on the contrary, if you have a long connection like this, the denominator becomes large. So this portion becomes small. So your shear lag factor is getting closer to 1 if your connection is long enough. So what does it mean here? It means that, yes, if you design the connection well enough, if you give it enough length, the shear lag should not affect the rupture strength of your member very much. This is what we can do. This is what we can control as an engineer. Okay. If you somehow have a very short length here and you have a problem with the shear lag, it also means that you can increase the rupture capacity by increase the length of the connection, just like this one down below. All right. So is there any question about this? Are you guys awake?
Hello, John.
Okay,
you
are awake.
Like some specific real life example on the internet.
Well, you're gonna have examples soon enough, young man. Just wait for a few minutes, okay? Now I have to point out one thing. Let me. Okay, this is the table. But before I get into the table, this is the table taken from AISC specification. Okay, so everybody can get a hand on that. You can see the problem with the shear lag is that when you look at this picture, we can only connect one element of the section. Okay, you can say that this angle has two legs. So the leg that sticks out in the air, you can say the Americans would call this the outstanding leg, OSL, outstanding leg. It's a leg that just stands out in the air. So in practice, nobody is going to try to connect that member, that element. I'm sorry. Okay, most of the time we are going to leave that leg free in the air. So the problem is that when we talk about angles, we have two legs, right? So we can say we have two elements. When we cannot, or when we do not connect all the elements of the section, shear lag will occur. It doesn't matter how you try to connect the member. It doesn't matter if you use bolts. It doesn't matter if you use welds. As long as you can, or you don't connect every element, you will have shear lag problem. Okay. For this example, you see, we connect one leg, which is this leg. We do not connect the outstanding leg. So we are going to have the shear lag problem. Okay, I'm going to give you more examples. Like, I don't know why I don't include the more pictures here, but let's say, hang on. Okay, that's it. Let's say this is the most common case that you can find. If you have, you're going to have the example about this. Don't worry. Let's say if you have the H shape or the Y flange, yeah, and sometimes because generally the manufacturer in this country, it means that each member is generally 6 meters long. Okay, that's how they manufacture the steel product. You can order them, but you're gonna have to make a huge order, and they can roll the members according to your need. But generally, they would do it like 6 meters, 9 or 12. But if you don't say anything, most of the products that you will find in the market will be 6 meters long. Okay, you cannot say I am going to design the member 9 meters long and then come on, we can buy it anywhere. No, doesn't work that way. The general length of each member in the market is 6 meters, meaning if you face the structure that needs to be 9 meters long, chances are you're going to have to connect two members together to form a 9 meter member. Okay, and when that's the case, we are going to need some connection that we call splice. Okay, so when we splice the connection, sometimes when you splice an edge like this, and you put two together, generally we would try to splice it like this because it's very convenient. Okay, that becomes your splice plate on top and then at the bottom. When your edge becomes small, sometimes it's going to be very, very hard to connect the members at the web. So we leave it free like that. For example, I think you're going to have the example of the H150 by 150 that I prepare. So yeah, 150 by 150, it means it's only 15 centimeters in depth, right? It's only this much. No longer than one elbow. So to try to connect in the area between this, it's very, very hard. So we deliberately leave this area without anything. So that means now you have the flange, the two flanges connected, but you don't connect the web. So this will fall into the category where you do not connect every element because you only connect the flanges, but not the web. So the shear lag is going to occur here. Or when you have the channel, the C channel, generally the channel is made in a way that its flanges are tapered, just like the IB. So when you try to bolt it somewhere around here, it's going to be difficult, right? Because the thickness of the flange is not constant. So most of the time we will try to splice the channel or to connect the channel through its web like this. So that means both the flanges are left free. So again, this falls into the category that you do not connect all the elements in the cross section. I may write more. That's a web not connected I don't know why I tried to write so small. Say that's not, okay? N looks like an H now. Not connected. See here are flanges not connected. Okay, it's practical not to connect them, but you know you have to pay the price. You have to check the shear lag, or you have to check the rupture. So, is there any question? Are we okay with this one? Okay, good. So now let's go back to chapter 2. Right. So this is the table that you get from the AIC specification. It basically says that, you know, here, blah, 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 all the tension members where the tension load is transmitted directly to each of cross-sectional elements. This is exactly what I just said, but they just perhaps say it in the slightly more confusing way, you know? Okay. If that's the case, I said transmitted directly, it means that you connect every element. It's the opposite of what I just said. Okay. If you, and they prefer the word transmit, but I feel like I like the word transfer more, because transmit is like you sending a signal. Anyway, if you connect every element, so we can go back here and say rephrase this. Okay, if I connect the web and the flanges, or if I connect the flange, the web here and the flanges, it will fall into the category where, you know, the tension load is transmitted directly to each cross-sectional element. In that case, you're not going to have the shear lag problem. Otherwise, you will have the shear lag problem. And this becomes the formula that I already mentioned, the formula where you need for the calculation of the shear lag factor. Okay, now, right. It's just more suggestions by them, because look at this picture. This is a picture of the plate, you know. The shear lag is going to occur when you weld the plates on just the parallel direction of force. If you weld, that's too big. If you weld on the end like this, in the perpendicular direction, the shear lag is gone. Okay. If you, I can write down. I'm sure of it. No shear lag. If you wear it like that. But you know, I think the reason that they have this is because the welders in the US, they command a very high fee. So you know, they don't weld if they don't have to. That's the point. Okay, and they would leave it to try to be economical, but in here maybe it's kind of cheap, so let's just go ahead and weld it. Doesn't matter. So let's say the numbers that they give here means that you don't have this. Okay, if you weld on both sides in the parallel direction to the force, you're gonna have 3 of this value. But see, you don't go beyond this. You don't go beyond L, which is the length of the weld here. W becomes the width of the plate, or the distance between the 2 welds. You don't go beyond L less than W. Okay, so you don't weld it shorter than the width of the plate. And if the length of the weld, you know, falls into one of these, and you just use the shear lag factor. And then they have more the formula for you to calculate the shear lag for this connection. See, this is in the old days, we used to connect the circular section or the square or rectangular section by using the gusset plate. Okay, you may wonder, what the heck is gusset plate? Gusset plate is the plate, but they just add the word gusset for I don't know why, just another plate. Okay, I was really confused when I was your age. What is it? What is a gusset plate? Why do you have to call gusset plate? Can you call it just a plate? Well, I guess not. Somebody just started calling it gusset plate. So, okay, it's gusset plate. Anyway, So because of the technology of the cutting process, and so it wasn't very, good back then. So when we want to connect the circular members together, you need to, attach the plate through the circular section like this. So that caused this section to have the rupture failure with the shear lag problem as well. And this is the suggestion that you can calculate the X bar and put it in the shear lag formula. Okay. And likewise, in the similar fashion, for the rectangular or the square section, the way to connect them in the past, you need to put the gusset plate through it like this, or outside like that. So they have the formula suggestion for you to calculate the X bar of this situation to put into the shear lag formula, which is this one. Okay, no more. But nowadays we have the software 3D cutting edge technology, so we can cut the members any way we want, so we may not need to connect them in this way anymore. So you may not find yourself using these formulas at all. Okay, and there's more here, that if you are too lazy to calculate, they have numbers for you. You can just pick anything you like from here, but according to the conditions, of course. Okay, so if you're lazy, but keep in mind that if you pick the numbers from this, web connected with 4 or more fasteners and so and so, and this is for the H shape, this is for a single angle, chances are these numbers are going to be lower than the number you get from the formula. Okay, because they want to be safe, right? Anyway, so that's it for shear lag. Let's talk a little bit more about the design of the tension member as a whole, because what we just mentioned up to this point is the strength aspect of the tension member. Of course, we have to make sure that our members will be strong enough to carry the force. That's the main thing. But another issue that you have to take care is also the limitation in terms of slenderness, because sometimes, you don't have a large force for your member to carry, but it just so happens that your member can be very, very long. So it becomes slender and it can wobble like that because it's just so long and slender. And when it starts to wobble like that, you cannot almost transport it anywhere, even in the factory, So they say for tension members, for the practical purposes, you should check the slenderness ratio, preferably not to be more than 300. Okay, let's say you can imagine, look at the reinforcing steel round bar RB6 maybe. Have you guys seen the real RB6? It's wobble, right? It's gonna wobble pretty much. When you just lift it up like that, it's just gonna, because it's so slender. But RB6 is light, and you can manhandle it. But when we talk about the steel product, the hot roll steel section, you're gonna have to lift it by something else, maybe the forklift, the crane, so and so. So when the slenderness ratio is greater than 300, it's gonna wobble. It can be dangerous. Okay, so that means, and R here is not the radius of the fillet. R here is the radius of gyration. Okay. And from time to time, you may find yourself have to take care of how much deflection on your tension member can be as well. So this is the basic formula from your days with mechanics of materials, right? PL/AE, that's deformation of the tension member or compression, right? It's a basic formula. And sometimes you have to take care of that. And the number that you should, limit your member Most of the time, it depends on the judgment. It depends on the requirement of your specific project. Okay, there is no number, no law given on this. Just maybe you know that, okay, we don't want our member to have deflection more than, say, 1 centimeter. So that becomes your limitation. So it's based purely on engineering judgment. So it would not be a bad idea for you to determine this kind of design criteria at the very beginning of the project. Okay, just to make sure that, okay, you are not only going to make sure that your member is strong enough, but you will also make sure that your member will be serviceable as well. Okay. Now we have like a few minutes left before the break. So no, this is nothing. Okay, let's take a look at the truss, because I didn't look at the drawings. I don't know, because Ajahn Sutat gave me basically it's like a 2-story building that we are going to convert into the steel design. I'm slightly concerned that we may not have a system of truss for you to design, because a truss is probably the most basic steel structure that you are going to deal with. And we mentioned about this the last time I can recall, top chord and bottom chord, in compression and tension, if it's a simple beam, right? And then the web. So basically, you either have tension members or compression members for the truss. If you can take care of tension members and you can take care of compression members, hopefully you should be able to design the truss, right? Hopefully. Okay. Now, we have so many configurations. I'm not going to go into details here. Now, the most interesting thing about the truss is this. I don't know if you have picked up from other classes, is that the configuration may dictate the type of force that you are going to have. So this is one configuration. Now we all know that the truss is a form of a beam, right? So this is basically a simple beam, and you have positive bending moment, meaning that your top chord is under compression, and then your bottom chord is tension. Now, with this, generally the vertical web is in compression. That's normal. But with this configuration, you notice that this diagonal web is under tension. Okay. Now, if I change the configuration from this on the left, now we know the diagonal web is under tension. But if I swap the configuration of the diagonal web into this, the one on the right, you now notice that the diagonal web is under compression instead. If you don't believe me, you can just go home and try to revisit your truss analysis from your good old days, right? And when this is under compression, you think what's going to happen? If you can recall, you should have a short lesson about the long column in your mechanics of material, right? So the longer the member, the less compression it can probably carry because of the buckling problem. So this configuration on the right has the longer member, because you can see diagonal member is always longer than the vertical one due to the distance, right? So now with this configuration, you have the longer member taking compression. So engineering wise, this is not very efficient, don't you think? While the configuration on the left, you have longer member under tension. As far as the calculation is concerned, up to this point, we always talk about Fy and Fu in tension members, right? Because as long as you pull the member, you're going to reach Fy or Fu one way or one thing or the other. So tension members are a lot easier to handle. And so you see that the configuration on the left here should be much preferable to the one on the right, because the one on the right put the longer member under compression. And you see, because the diagonal and vertical webs will take care of the shear, and the maximum shear is around here at the support, right? And you have the biggest force in the web around here. And you can see the thickness of this is the magnitude of the force. So now you are using, you know, the longest member to take care of the largest force. So not very good approach, I'd say. Any question? And likewise, the same thing here. See the configuration on the right here will give a longer diagonal web tension. Meanwhile, this one will be under compression instead. So the selection of the truss configuration would help us, you know, dictating what kind of force we have to handle as well. Okay. So we may have so many things, you know, tension members. I may exceed your time limit for a few minutes, so that this is, you know, end beautifully. Okay, just a few minutes. This is a three-dimensional truss. You know, nothing. You have the software to handle this now, but you know, in my time, when I was your age, computer software just became available, and there was no way we could design something like this. Got to improvise, you know. Okay, and this is the tension members that we have seen before, just like for the bracing system. You're gonna have tension members in that. And here it's a very smart design, right? You put the larger force under tension. So this becomes the suspension bridge that can take a large load, because the force in steel is now in tension. Like this one, you know, all the support reaction in the middle comes down here. And then the whole thing is supported by cables. And the cables can be made very small, right? Because the force is tension. In the end, it's kind of a beautiful design that takes advantage of the nature of the force, right? Okay, no, that's the same thing. Now, just small things I'd like to mention. Now, when I was in the US, funny how, because Ajahn Suthat also got his degree from the US, different universities, but pretty much the same concept. In one of my class, they gave the assignments to students to say investigate the collapse that happened before, and we got to do the presentation in front of the class about the collapse, just to raise the awareness amongst engineers. And what we do, you know, if we are not good enough, if we are not careful, you know, bad things can happen to other people. And that's why we need to have license, like I said. See, 114 dead, 114 dead, more than 200 injured. Because this is the collapse of the walkway in the hotel. Now, it used to be around, that's a walkway, I'd say, yeah. And they had a party on that one. So the load was full, you know. And then the cable here just ruptured. So the whole walkway just fell down. Boom. So you know what happened? What happened is this. This is the original design. The cable goes through nothing because the tensile force is here. So if you design the cable properly, it should be okay. But they say, okay, this it's difficult to construct. So they change the detail into the left one. You notice the difference? You guys notice the difference? Now these two cables do not coincide, you see. So this will cause torsion, correct? Because the force is here. So that will cause torsion. Basic free body diagram. And the problem is that this member was never designed to take that torsion, because the original design was this. So this small torsion that occurred here because these two forces did not coincide was more than the member could take. And from this original design, now you add torsion, boom, it collapsed. And it just so happened that the kind of collapse like this would not occur when the load was light. It had to be the full load, right? So there was a party, a lot of people, and then this collapsed, and the whole walkway dropped down. Okay, right. That was then. Okay, and then that's the collapse. Very, very sad thing indeed. Okay. All right. So that's the end of the lecture for this. Next session, we are going to start the example. So you see the practical ones right away. So, okay. Let me stop the record first.